All right, so LTE frame is similar to other wide area network frames, such as we have seen one before, which was 802.22. LTE frame consists of several superframes which are 10 millisecond long. Each superframe consists of 10 subframes which are 1 millisecond long. Each subframe consists of 2 slots which are half millisecond long. All right. Why 2 slots? Because one goes up, one goes down. Uplink and downlink. So basically, in 1 millisecond, you will be able to speak to the. I mean, uplink is down. Okay, this may the order may be wrong. In 1 millisecond, you will be able to listen to the base station and then and also send something to the base station. Okay, and the order may be wrong, so I got to make a note of it. Can I have a pen? Today is not my day. So D-link generally, downlink generally comes first. Okay. Then this slot consists of 6 symbols. Actually 7 symbols, 0 through 6, and there is a cyclic prefix before each symbol. Right? The first, there's some space left because of 0.5 millisecond, there's some extra space left, so the first one is slightly larger than the other 6. So it is 5.2 microsecond for the first symbol and 4.7 microseconds for the others. All right? So there are 7 symbols. However, there are situations where we need even longer prefix because we are going farther distances. Okay, remember the cyclic prefix takes care of the multi-path delay spread. If you come directly and you come through a reflection, those will collide and you will lose part of the symbol, and that is the part that is covered by the cyclic prefix. And so some situations, so there is extended cyclic prefix. In that case, we reduce the number of symbols to 6, and everything is longer, 16.7 microsecond. Cyclic prefix. All right, and so this is the normal, this is the extended, and you can see that basically uplink and downlink in 1 millisecond, and that is one of the key things about LTE is that it is one of the fastest to get. I mean, you can just the cycle time is 1 millisecond, which is basically in 1 millisecond you can get to the base station every millisecond, as opposed to the previous technologies which have 10 millisecond, 20 millisecond, and so on. Right. Now, there could be any number of subcarriers, could be 10,024 or 2,048 subcarriers. So there are too many subcarriers, and if we gave one unit of 1, that means too many combinations to give. Right? So they decided that the combination will give in the units of 12 carriers at a time, subcarriers at a time. Units of 12 subcarriers at a time. And then there are symbols, and they decided we will deal with 7 symbols at a time. So you cannot get 3.5 symbols, or you cannot get 3 symbols, or you cannot get 4 symbols. We give you 7. Similarly, subcarriers, you cannot get anything less than 12. You cannot get anything which is not a multiple of 12. So you get 12, 24, 36, 48, and so on and so forth. All right. So you get what we call a resource block. A resource block is 12 subcarriers by 7 symbols, and each of these little squares is called resource element. So this is basically 1 symbol in 1 subcarrier. So you can put any information in that 1 symbol in 1 subcarrier, and you get 12 times 7, 84 such things. Actually, you cannot put your data on all 84. That, as you will see, some of these are for pilots. Okay, and the name for pilot in the case of LTE is reference signal. Okay, but I call it pilot because it's much easier to understand. We have used the word pilot before, but you won't find this in the LTE literature. Okay. All right. So if a station, so basically, since there are 12 of these, you can see that in 1 slot you will have if there are 20 megahertz channel and you have, let's say, 2048 divided by 12, whatever number comes out, that many resource blocks are theirs, and we can give it to that many users, and so on. Obviously, we cannot give half a block to anybody, and so, you know, and so that is the unit. Now, the carrier spacing is 15 kilohertz normally, but it is reduced to 7.5 kilohertz when we do multi-cell MVMS. Now, I did not have a slide on MVMS and LTE, so I have put it, I first put it in LTE lecture, and then I said, well, all the numbering will be wrong, so I put it in the LTE advanced lecture. So we will explain to you what is MVMS. MV is multimedia broadcast and media broadcast and multicast, something like that. Okay. So when we do media broadcast and multicast, which is basically TV or something like that, which is going to everybody in the neighborhood, then we don't have to do it from one tower. We can do it from multiple towers. Okay, and the same information goes to everybody. So then we can even use that facility from two towers. You can get the signals at the same time and combine them, right? So that's why in that case, there is a lot more flexibility available. And just for that time when we are doing MVMS, we can reduce the carrier spacing to 7.5 kilohertz. So more carriers tightly packed. So they are optimizing in every sense. In fact, one thing I forgot to mention before, and then I realized when prepping LTE advanced lecture, one of the biggest thing that, you know, most of the newest thing do is that they have a reuse factor of 1. Remember the first diagram when we started the cell networks, we said, well, you will not use the same frequency in the next cell and then maybe 2-3 cells apart. Well, those are past days. Now we use the same frequency everywhere. Okay, so 2 cells next to each other may use the same frequency. Okay, and now the problem is clearly at the edges, right? So reason I was bringing all this up is that they have optimized every single drop that you could get from the spectrum. The spectrum comes in billions of dollars and millions of dollars, and therefore we don't want to lose any of it for whatever reason. So similarly here, 7.5 kilohertz is this kind of optimization, because if I can bring you TV in a faster with less time and less spectrum, why not? Okay, and you saw that extended too. And basically, normally they will use that normal prefix, normal cyclic prefix, but there are situations we have to extend it. So they have, you know, special cases like that. Okay, so here in the normal case, this carrier spacing is 15 kilohertz. There are 12 carriers and 7 symbols in the resource block. And this cyclic prefix is 5.2 and 4.7 as we saw in the previous picture. In the extended case, the subcarrier spacing is 15 kilohertz. And when we give you 12 carriers and 6 symbols. Why 6? Because that is how many we can fit in one slot. And the cyclic prefix is 16 microseconds. Right? And in the case of MVMS, the subcarrier spacing is 7.5 kilohertz. We give you 24 subcarriers at a time and 3 symbols, because the cyclic prefix time is 33.3. So even bigger, because the reason it is even bigger is because now you are getting signals from many towers. Some towers may be far away. Okay, so the multi-path spread is much more larger. So we need bigger cyclic prefix. And to make up for that, basically they reduce from 15 to 7.5. Now, this is what we call, so far what we have discussed, the type 1 frame. This is type 1 frame. There is a type 2 frame, which I am not going to discuss in this class. It is used in TD systems compatible with TD SC-FDMA system. Okay, I mean there's more detail there which we don't need to go, because, you know, in that country basically you will figure it out what that is. and it's not a big deal. Okay. Then, okay, so that is all about the frame. Now, in the frame, if you look at these frames, there is one slot. Obviously, there are many resource blocks, and they're going down and then up. Some of the symbols are reserved, or some of the elements, resource elements, are reserved for control. And these are called control channels, because you take the symbol from this frame and then take the symbol from the next frame and then take the symbol from the next frame, that those symbols can be combined to form a continuous bit pattern, which is called a channel. Okay, and this is again a telephonic or a telephonic trick which we don't play much in the data world. In data world, the packet bits are independent. When you send a packet, you don't expect that you have received packet 1 and then you combine the packet bits from here to there. But this is circuit switching world where this was very common. You know, you had a circuit and you had a virtual circuit. So this is like a virtual circuit where you get this byte and then the next byte and the next byte and the next byte later on. Okay. So the idea is that many of these symbols here may be reserved for control, and they form a channel. Why they form a channel? Because successive frames, bytes or symbols will be combined to form some information. Control channels. So there is first control channel called DCI. And DCI carries the downlink schedule, uplink schedule, power control, supported MIMO, etc., etc. Now, this is very similar to what we discussed in 802.22, where when you started, the very first thing was, how does this frame look like? You know, what are the different users, where the user 1 begins, where the user 2 begins, and you know, what is the modulation, things like that, right? So the same thing has to be done here. But first thing is, the very first symbol says DCI, which means it tells you everything about the network. So if you get this out, at least you know which network you are on and what kind of MIMO and things like that they support. If you get this, then you can basically decode the rest. So this is part of this symbol, this information is part of what they call PDCCH, Physical Downlink Control Channel, PDCCH. And this is the first few symbols in each subframe. Then comes PDFICH. Now, I don't think I can remember any of this acronyms, but the key idea is that there are control channels, and the first control channel is the downlink control, and then there is a downlink format. I mean, actually, there isn't a downlink because this format has both uplink and downlink. So then, once we figure it out, then we can figure out as to what is the downlink rest of the stuff. So it will say that user 1 begins here, user 2 begins here, and for the uplink also it will say the same thing. User 1 should begin here, user 2 should begin here, and this is the modulation they should use. These many antennas they should use, and they should direct to these antennas. So all that information, the schedule information, is in these control channels. And then there are more control channels, and I really don't want to go through them here again because you won't remember and I won't remember them. All we need to remember is that there are control channels. Okay? And then there are data channels, which are called transport channels. Okay? So the data channels are called transport channels and traffic channels. Either name. So the transport channels, basically whatever is left, minus the reference signals. You know, all the way through in the middle there is a reference, you know, pilot signals. So given that you might, some part of this is control, and then rest is transport, and so on, right? And then there is some pilot. All right. Any questions so far? Is it making sense a little bit? Because I think we finished them. We finished wireless regional area network, and I think if I put this slide next to each other, and this is the problem, if you forget wireless regional area network, which you have forgotten because it's done, now, this question, the same thing comes back here in the different form. But it is very similar. In WRN, we had, exactly the same thing. We had, the names were different, but first there was a format, and then, different kind of format, and then users, the database started. So here there is a control and then transport. Now broadcast and multicast. So broadcast channels information, basically all the information to join the system. So one of the broadcast channels is just the announcement. So it's not TV. It's just the announcement that this is AT&T network. Okay. So it contains all the information needed for the users to join the system, e.g. bandwidth, antenna configuration, pilot signal, power, etc., etc. And there is no HARQ on the broadcast. What is HARQ? Hybrid ARQ. So this is where you keep the old information and combine with the new information, right? As opposed to pure ARQ, where you throw away the old information, just use the new information, right? So here we don't have any retransmissions, no ARQ, no HARQ, no acknowledgement. If you didn't get it this time, just wait for the next time. And we use the best modulation. Best means most robust modulation, QPSK, just 2 bits per symbol. As opposed to 16 QAM or 64 QAM or anything like that, we just use QPSK. Simplest thing. Then multicast channels, broadcast. Multicast channels is basically TV. And that is basically whoever subscribes to it will get it. So this is why it is multicast. And multi-cell transmission from multiple base stations, and uses extended cyclic prefix. So this is that other channel, MDMS channel. Now the pilots. Now, if you read the standard, for every kind of situation, there is a different set of pilots. Okay, so again, I wouldn't go into details of where you exactly put the pilots, because it depends upon the situation. How many antennas you have, how many base cells are, how they're intertwined and all that. So all the information has to be clearly known before I can tell you where the pilots are. But this is a simple example. So here what I have shown is, if you can see somewhat, and this is a checked copy of the picture, is that anything that is hatched is a pilot. And they call it reference signals. Okay? Some of the pilots are basically common in all situations, and some are special. So somewhere it says R0, R1, R2, R3. So this says that this is a pilot from antenna, ith antenna. So whenever you transmit from the antenna number 0, you put the pilot there. When you transmit the same information on antenna number 1, you put the pilot there, R1. So when somebody gets that signal, they can figure it out where it is coming from. Alright, that is how the MIMO is done. Okay, and so the pilot location. One thing is that the pilots are spread all over. Why they are spread all over? So that you can get the. So we don't know what is happening on this frequency, for example, but we know pretty close to what is happening there because we know this frequency. Right? So you spread it uniformly along the y-axis and you spread it uniformly along the x-axis. Now it is not random; it is fixed. So basically, as shown here, every 4th carrier has a pilot. As shown here, you see almost every 3rd or 4th carrier has a 4th symbol has a pilot. Alright, so not before too much time, because the thing is, if you wait too long, the channel will change. The wind will blow at a different speed. The sun will be there at a different location. The temperature will be different. Right? So every microsecond, millisecond, things change. So you have to do it, very often. So we are really squeezing the last bit, as I said, is that we need to know the exact channel at the exact time, and we use that information right then and there. Okay, so what are these four things here? This is antenna port 0, antenna port 1, antenna port 2, antenna port 3. So basically, there are four antennas and we call them ports, because when you look from a distance, this looks like one antenna. You may not be able to see the ports, but there are four signals going. Okay, and they have tried to show here one full subframe, that means 12 symbols, sorry, should be 14 symbols, okay, and 12 carriers. Okay, is it clear as to why pilots are there and where they are, right? I mean, they have a lot of information in them. The information is fixed. So there is, so basically, if there is an error in some pilot at the receiving end, then it knows that there is a noise at this particular frequency and particular time. And depending upon how good that signal is, it will tell that please reduce the rate at this particular frequency and particular time. All right, moving on to protocol stack. It has, now this is only a data link, right? This is not, on the top of this LTE, you probably have IP. So only layer 1 and 2, but there are 5 sublayers. If you want to be exact, there are at least 4 sublayers, 1, 2, 3, 4, and then there's a control part. All the control goes through the radio resource control and then goes through this, and the user plane has 4 parts: packet data convergence, PDCP, radio link control, RLC, media access control, and file. Okay, so total 5. And I'm going to describe each of these sublayers in little bit more detail in a minute, in this next. First thing is the radio resource control. So this one basically makes sure that everybody gets to the right base station, that they're not wasting time on the air. So basically control plane functions of paging, connection, disconnection, mobility management, and QoS management. All right, let's understand. What is paging? Paging means that I know you are here, but we want to make sure that you are here, so we page you. Right? So this is a signal which comes from the base station which says, hello 314-322-8092, are you there? And wake up and answer me. That is paging. Connection is obviously I want to connect to you, either the base station or the telephone says that. Disconnection is same thing. Mobility management is basically handover. Where you are driving, you say, well, I want to connect to tower 2 now. I'm getting better signal from tower 2. And then this message goes to some place where they decide, yeah, you should go to tower 2 or not. That is mobility management. Meta, is it? No, not Meta. Can you poke him? Yeah. Here. Yeah. So basically mobility management, right? And then QoS management. QoS management is basically making sure that if you are doing video or voice or data, whatever we agreed with you, you are getting that. Time and delay requirement. Your throughput is being met, your delay latency is being met, and everything. All right. So that is radio resource control. Then the next layer down is PDCP, and PDCP does 4 things. First thing is there is header compression. So what is header compression? Well, the packet that has been given to you has an IP header, a TCP header, a application header, and much of this is repeated anyway. Right? So we don't want to send that on the wireless because we just don't have that many bits. So we compress it. Okay. And there is an IETF RFC called ROHC, IETF Robust Header Compression, which tells you how to do this, because most likely your source is same as before, your destination is same as before, your most of the other fields are same as before. If they're same, just put a 1 and then you're done. Right? And so instead of sending 32-bit IP address or 128-bit IP address, you can just put a single bit and be done with it. Right? So that is header compression. Second thing is integrity. Integrity means nobody has changed the data, and so that can be done with CRC, but not here. We are doing it with message authentication code. So this is secure CRC. Right? In CRC, what happens is, actually CRC is very simple. CRC is a plain division. You give a number, divide by something, and the remainder, whatever comes out, you add to it, and that is your CRC. So the number that you get is always divisible by that. If it doesn't divide, then you know there is an error. So simple. The problem with CRC is that the divider is known to the world. It is written in the standard. This is the number you divide with. Okay? So all you do is message authentication code is that you take a random number and you somehow tell the other side that this is the number we are going to use. Okay? Now nobody knows it, nobody can change it, and now you have a secure CRC. Of course, there is a little more complication, but for now it is sufficient to understand that message authentication code is a secure CRC, which is generally a division operation. Ciphering. Ciphering is another name for encryption. So this one will encrypt. Again, the key is required, which is exchanged with the other side, and then you encrypt everything, and it is decrypted at the other end. In sequence, the delivery and duplicate elimination. So everything is numbered, and everything is delivered in that order in which it was received, and in which it was received from the sender. And if there is something received twice, it is removed. So this is very simple. Basically, this layer is security and integrity, right? PDCP. RLC does three functions: segmentation and reassembly, aggregation, and out of order. So basically, if you really don't think about this one, then all it is doing is segmentation and reassembly and aggregation. Segmentation, if you get a big packet, we divide into pieces, and at the other end we combine them. That is segmentation and reassembly. If you get very small packets, then you aggregate them. Right? It's opposite of segmentation. Right? So that is the thing that it does. And we are out of order PDUs, and basically, and then ARQ. If something is missing, then this is the layer that will do ARQ. Who does HARQ? Phi and MAC layer. ARQ is done at this layer. Okay? At this layer, basically it says to the other side of this layer, say, I didn't get it, and that layer will transmit the whole packet all over again. So this has no idea of the quality of the signal or what was received at the phi layer, nothing. It just has the whole packet. It doesn't even know which bits are wrong, nothing like that. So basically it deals with the whole packet, and that's why it does only ARQ and out of order PDUs. This one is in three modes. Transparent mode, where there is no segmentation and no header. Unacknowledged mode, in which we don't worry about the acknowledgement or ARQ. So there is no, so basically unacknowledged mode means there is no acknowledgement, no retransmissions, and this is what is used for voice and video. And then the acknowledged mode. Acknowledged mode is what we talked about, is that you get the acknowledgement and you have ARQ. And the packet looks like this. So the first bit tells you whether it is a data or not. It could be a control. And this, actually the next slide will explain all of this in great detail. So you just stay on the next slide and this slide. Okay, so this is a picture and the description is on the next slide. So resegmentation flag is whether this is a full PDU or segmented PDU. Actually, I would have called it just segmentation flag. Okay. Polling bit is whether the transmitter requests a status report. So the transmitter could just set that bit and then you say, well, you know, this was wrong. I mean, this was not received correctly. So this is basically polling bit is also like, you know, I need the ACK. All right, going back. Framing information, SDU is segmented at the beginning or at the end of the data field. So this is the framing information which tells you that where the segments are, and the segments could be, the data field begins, the segments could be here or over there. So that is the thing. And then extension bit follows set of extension length, and I will come back to that slide in a minute. Sequence number is the sequence number of the PDU. So there is an extension bit, and that tells you whether all these bits are present. And the serial number, sequence number is that, and the last segment, is simply says that this is the last segment and end of the previous PDU. And the segment offset says that this segment fits where in the PDU. So you have a PDU, you get into 4 segments. First segment has an offset of 0. Second segment has an offset of whatever the first segment was. Third segment has the offset of first plus 1 and 2. Right? So you know that way that when you get this segment, where to put it into your buffer. Segment offset. E1, L1, E2, L2, EK, LK. So there are variable number of these E bits, and they are called extension bits. Whether a set of NAC, E or E2 follows, and whether a set of SO start and SO end follows. SO start and SO end are the beginning and the end of the offset of the last segment. So this is basically an acknowledgement. Okay, a negative acknowledgement. So it says, well, I did not receive the segment number 3. I did not receive the segment number 5. I did not receive the segment number 7. Okay. For 3, the offset was this. For 5, the offset was that, and so on and so forth. So all those things are indicated here, E1, L1, E2, L2, EK, LK. So this whole thing is not part of this packet, this is part of the acknowledgement. Okay, so I have my buffer and I put all the segments that I've correctly received in my buffer. So in that sense, it is, in IP also we do this, and that is called selective ACK. So this is a selective ACK, and actually it is much, I think in IP, if I remember correctly, you don't really acknowledge a segment. And we call them, there's another name for that over there. But here, they're acknowledging the segment. I think we call it fragment in IP. So we don't acknowledge the fragment, but, you know, so anyway. Here, SO start is simply the beginning and the end of the last, remember the LOST, not LAST, right? LOST means that this I didn't get it.
So it's for each lost segment?
This, you send all of this stuff for each of the last segments. That's why there are K of them. All right. So summary of this. Let's summarize what are we doing. So radio link control layer is responsible for segmentation, reassembly, aggregation, and retransmission. And that's why it has all this extensive acknowledgement field there, and then basically indicating where the data comes in and goes out, and basically, and you can acknowledge very selectively. Now, all this could be part of MAC. For example, there's no reason that we could not call this part of MAC, but this was a function that they felt was totally separate, nothing to do with the rest of this stuff, so they put into a separate layer RLC. Now, MAC is coming in a minute. Similarly, even PDCP could be part of MAC. Okay, but again, this is something that they felt, oh, this is separate, and so this is done separately. Okay, RLC is done. Now the MAC. MAC has three functions: multiplexing, scheduling, and HARQ. HARQ. Some people call it HARQ. So multiplexing means that you have many people going to the same direction. We put them. So this is aggregation, another name for aggregation. But you see, this aggregation is different from the previous aggregation. Here we might have a control channel, control message going to somebody saying that, you wake up or something, and then the data packet and so on and so forth. This is basically from maybe different channels, let me put it this way, coming in here, right? And then header itself has many subheaders, and for each subheader it tells you what is the channel it is going on, right? So basically its job is mostly multiplexing. So this is all multiplexing part of it. Transmission scheduling is the other part. So basically MAC has to decide how many bytes you get to transmit or how much time you get to transmit. That is part of this same thing here, MAC. This might also decide as to what frequencies you get. But if nothing else, it could decide at least the number of bytes you get, and then maybe phi can decide what frequency and how many symbols. But here it could decide that you need to transmit 2000 bytes. HARQ is also done here. So basically, if something is not correctly received, this collaborates with phi. So basically, because of HARQ and because of many of these things, the line between MAC and phi is not very solid like in other protocols. MAC has an extension flag. So there are 4 fields in the MAC, if you notice in the bottom line. Extension flag, if you go back to the previous picture, and all that says is more subheaders follow. So there are many subheaders which are variable number. So this more bit will be set, more bit will be set, more bit will be set, and that is called extension bit actually. So more bit will be set. I think the name should be more, it will be much easier, but the last one will say this is the end, 0. Channel ID is clear. Format indicates that the length, the size of the length field. So the format is again misnomer because it is the length of the ID field. ID field could be 0 or more than 128 bytes. So this is variable length field. And therefore, if it is less than 128, we put a 0 here in the format field. So this is not the length, I'm sorry. Length is here. Length of the element, SDU, length of the element. And so the length field is here. Now the length could be less than 128 bit or could be larger. So, 128 can be presented in 7 bits and therefore 1 byte. And if it is longer, then we need more than 1 byte. So this is, format is simply the length of the length field. But it is, it is coded very strangely. 0 means 1 less than 128 byte, and then so on and so forth. Okay. Right. So we know the MAC, RLC, radio link. Okay. Now we go back to the last one, which is the phi. Phi actually we already discussed so much in detail, so we don't have a slide on phi. Any question about any of these layers? Just to remember again, this is basically the paging and mobility. This is security. This is retransmissions. This is scheduling.
For the RLC,
yeah.
the HRQ there is just for the lost PDUs or
Right. So if Mac didn't fix it, then it won't give it to you. Right? Whatever it didn't get from Mac, then it will just ask for the retransmission.
it's just that if the HRQ doesn't work,
Yeah.
it
Yeah.
has a safety.
Okay, no, there are two situations. One is that some implementation may not implement HARQ. Okay, in that case, this is the only last thing. In some implementation, they implement HARQ, but after 2 or 3, they don't have any more punctures to send. They didn't puncture anything left. Remember how HARQ works. You don't send the bits in advance, right? And it didn't work, then you just give up. Good. I added this slide as a cartoon, actually more as a cartoon. And so you don't have this in your package. I just added last night. So I have already described to you whole WiMAX, because WiMAX is very similar. So what is WiMAX? What is LTE? You know, I mean, there are two kinds of networking people, net heads and bell heads. All of you here are net heads. I will tell you why. Because you have never worked for a phone company. All right? You always think in terms of bytes and packets and data. But if you were a bell head, you always think in terms of voice, circuits, bits, okay, and synchronization and rates. All right, so networks are designed very differently. Up until 4 or 5 years ago, those guys didn't know that the packet existed, and we didn't care for the, all this voice stuff. And so the networks are designed very differently. Net heads and bell heads. Now they're coming together. So this year, I couldn't say that if I go to Bell Labs or if I go to AT&T, I can talk and they can understand me. But before, it was difficult. All right. So WiMAX is a product of net heads. It did not come from the phone company. It came from Intel. It came from people like us who designed Ethernet. Okay? And the people who were there in the phone company didn't like this. The people who controlled the market of the phone company did not like this. And Qualcomm, for example, controlled the 100% market of the phone companies. They controlled the 100% market of 3G. They did not like that WiMAX comes in and they lose the whole control and Intel takes over. And so finally they designed LTE, which is same as WiMAX. But, this SC-FDMA, big deal, and so with that, we have WiMAX and LTE. So I didn't put a lecture here on WiMAX, but you can go back to my 2010 class and read all about WiMAX. It will be a repeat of everything that we said here. All right. So these are the key points. Very similar but very minor differences. Net heads versus bell head design. Enterprise networking versus carrier networking. The companies would love it. If you were to put your own network in your own backyard or in your own campus, WiMAX would be much easier for you to do than LTE. That's why every university professor who is working on wide area networking is working on WiMAX. Even today, 2014, when there is no WiMAX in the real world, right? Because that is easy to do. And carrier people will obviously are giving up fast. Academic versus telecom. So this is of academic interest, this is for telecom. Intel and Google versus Ericsson and Qualcomm. That's the difference, basically. Who gets the money? All right, both use OFDMA, both are incompatible with 2G, 3G, CDMA, etc., etc. So it has nothing to do with the previous. You cannot take a 3G radio and have it understand OFDMA. No way. All right. And if you are going to put two radios, 3G and 4G, then you guys have to put WiMAX. Right? So there is no difference. So that is the kind of thing, right? Quad band versus pentaband. So basically, now, they are moving to 5 bands. You buy 4 band radio now because now this LTE has a totally different band. So now you buy pentaband radio. And so that's all. This is basically, more of a commentary than information. So that brings us to the summary. 5 key points. First thing, you understand that the 4G, which is IMT advanced, requires 1 gigabit with 100 megahertz and 100 megabits for mobile. WiMAX and LTE are both 4G technology, pre-4G technologies. The next generation will be 4G. So we will talk about LTE advanced next, which would be 4G. WiMAX and LTE have numerous common features, and this was the last cartoon. Many bands, so both of them work on many bands. So you can take, 700 megahertz, or you can take 2.4 mega, and not 2.4, 2.1 megahertz, 3.5 megahertz, and there is a standard for that. Many bands, flexible bandwidth, you could have, this much bandwidth, this much bandwidth, this much bandwidth over there. Okay. FDD, TDD, frequency or time division duplexing, MIMO and beamforming, HARQ, IP based, both of them are IP based. That's another good thing. OFDMA, the key differentiator is SC-FDMA. Okay. Which is actually a special case of OFDMA. That is called DFT, pre-coded FDMA. And the argument for that is pepper. Puncturing now, so moving on, puncturing allows some ECC bits to be not transmitted. Allows some to be not transmitting. No, to be not transmitted. Okay? And so basically you create maybe 3 bits ECC, but send only 2 or send only 1. So that is what is called puncturing. And this is how HARQ works, that if you send extra bits, you are doing retransmission, but not full. STBC requires transmitting redundant symbols from multiple antennas. STBC is the space-time block coding. In the space-time block coding, from one antenna, you send some symbols. From the second antenna, you send some other symbols which are related to the first. Okay, like conjugates. If you remember that, right? S1 star, S minus S2 star, and so on and so forth. That is STBC. SFBC requires doing that on different carriers. That is space frequency block coding. Then the fifth thing we talked about is the stack, which consists of RRC, which is the radio resource control, EDCP, which was that convergence protocol, which does the encryption and compression, RLC, which does segmentation and reassembly, and the MAC, which does the scheduling. Okay. Now, reading list. I have added 3 more reading lists on the more than the handout you have. And I think you had 2 in your handout. I have 2 more 3 GPP, which I found yesterday. So when I was making the lecture for LTE Advanced, I thought that they had a very good information. 3GPP itself, the website, if you go to 3GPP website, they have an LTE and EPC, which is worth reading.